Okay, so in order to do a dynamic analysis on the boat, we need to first of all understand the forces that are acting on the boat. And when the boat is static in the water, the forces are essentially the weight of the boat acting downwards and the buoyancy force acting upwards, keeping the boat at that position in the water. We know that the buoyancy force can be calculated by multiplying the density by the displaced volume of water by the acceleration due to gravity. But if we were to sum up the pressure forces acting on the hull of the boat beneath the surface of the water, we can calculate the buoyancy force that way. So this illustration here tells us that each of those pressure forces can be expressed in terms of a localized pressure and localized area over which it acts. So we sum all them up, we get an equation that looks like this, and that also equals the buoyancy force. And this theory, by the way, is outlined in a documentation called the Lab 3 Dynamic Response, and it's up on Loop. When the boat is moving through the water, the forces change. It is now subject to a shear force that's acting in the opposite direction to the movement of the boat. This illustration here tells us that the shear force is proportional to the velocity gradient that's acting perpendicular to the hull of the boat surface. And here in this illustration, it's telling us that each of those shear forces can be expressed in terms of a localized stress and a localized area over which it acts, and that we can calculate the shear stress by using the dynamic viscosity mu. But ultimately, what you need to know is, if you're to sum up all those shear forces and pressure forces acting on the hull of the boat beneath the surface of the water, you would get what's called the total hydrodynamic force here. Now, the total hydrodynamic force is represented by this force vector acting upwards and to the left in this illustration. And if we were to resolve that into its horizontal and vertical component, the vertical component is essentially the buoyancy force, and the horizontal component is the drag force, which resists the movement of the boat through the water. Another force that we're concerned with is the propulsion force. It's provided by your pump, and it's used to overcome the drag force and propel the boat forward. So ultimately, the point we're trying to get to here is to introduce the propulsion force and drag force. And what I'm going to do now is I'm going to derive those two forces, and then we will use them in an equation to help us calculate the velocity of the boat as it moves through the water. When we look at the drag force, it's simply 1/2 times the coefficient of drag by the density by the frontal area of the boat by the velocity of the boat squared. So let's look at a couple of those values and explain what they are. If you can imagine the nose of the boat coming towards you, if you were to section the boat so that it's at its widest and its deepest, consider that cross-section area and then consider the portion of it that's below the surface of the water. That's your frontal area, and that can be obtained from your CAD model. The other parameter that we need to explain then is the coefficient of drag. The coefficient of drag is a value that's obtained experimentally for standard boat shapes, and also it's outlined in tables like this for standard shapes like smooth cylinders and spheres. Your design kind of falls between the two. It's fairly customized, so it's not a standard boat shape. So what you can do is you can use this simple table here to calculate the coefficient of drag. So the first step is to determine where you think the beginning and end of the nose of your boat is, so where it begins and ends, and calculate its length, and then calculate its widest part. Divide the length by the width, and you will get the aspect ratio. And the aspect ratio will give you a position along the top of the table here, and the value underneath is your coefficient of drag. So you may need to interpolate between these values or even extrapolate on further. So an example there would be a canoe. A canoe has a long nose and it's quite narrow. So divide one by the other, it'll give you a large aspect ratio and therefore a low coefficient of drag, which makes sense because a canoe is designed to minimize drag and cut smoothly through the water. Okay, so on to the propulsion force. The propulsion force has a little bit of kind of abstract and complex derivation here, but ultimately it comes down to quite a simple equation. So bear with me on this. So we'll introduce the concept of a control volume first of all. If you've got a pipe system, rather than applying the theory to the whole pipe system, you can pick a relevant section of it and apply the theory to that instead. So it's strictly defined as a space or volume that we focus our attention on for analysis. So if we want to know, for example, properties like the forces acting on the fluid system within the control volume here, we can use Reynolds transport theorem. And Reynolds transport theorem basically takes laws that have been designed or applied to systems and help us apply them to control volumes. And this tells us that the forces acting in the fluid system here equals the time rate of change of momentum of the fluid contained in the control volume. That's essentially mass by acceleration, plus the rate of momentum flow out of the control volume summed over all the outlets, minus the rate of momentum flow into the control volume summed over all the inlets. So we're looking at the rate of change of momentum through here, and we're looking at the difference in momentum from here to here as well. And that is one way of calculating the forces. The other way of calculating the forces acting on the fluid system in the control volume is by using this equation. So we're looking at the pressure forces at the inlet and the outlet, and we're looking at the forces transferred to the fluid in the control volume by the solid surfaces along here and along here. So sum all of them up and you'll get the forces acting on the fluid system in the control volume. So two expressions calculating the same thing. If we were to combine these two and transpose them to get this bit on its own, that's essentially the propulsion force. But bear with me till we simplify it a little bit further. Here we have a nozzle, and it's connected to the end of a pipeline by a bolt and flange arrangement. And we know that the nozzle is used to increase the velocity of the fluid coming out of the pipeline. And one reason why we would make this a control volume to try and calculate the forces acting in the nozzle would be to try and size these bolts. Because if the forces are too large and the bolts are undersized, the bolts can shear and away comes the nozzle. So applying the Reynolds transport theorem to this situation, we're saying that the rate of change, that the momentum is steady, so that there's no rate of change of momentum in the situation. And we're also assuming, so the first term cancels, we're also assuming that the mass flow rate stays the same, so we can take this out of the equation and represent it like this. So the forces in here can be measured by multiplying the mass flow rate by the change in velocity. We can also expand on the pressure term in here by representing the pressure forces at the inlet in terms of the pressure here multiplied by the area, and the pressure forces at the outlet by the pressure multiplied by the area here as well. So we put that in there. We let this equal this and transpose it to get the forces being transmitted by the solid surfaces on their own. And this is what we come up with at the end. And this is effectively our propulsion force. But let me elaborate on that a little bit more. Here we have a 180-degree bend, similar to many of your designs, where you've got the velocity coming in, you've the pump maybe situated around here somewhere, and the velocity going out. If we were to employ a Cartesian coordinate system like this to the design, we'll see that the inlet velocity is going in the negative x direction and the outlet velocity is going in the positive x direction. What that does to a Reynolds transport theorem is it means we add the velocities, so we maximize the velocity effect here. In this part, we look at the pressure forces at the inlet and outlet. In this example, it's assuming that there's atmospheric pressure acting here and here, and the delta P's are just taking any localized pressure difference into account. And that term is expanded on further. And this is the two of them combined to get the forces transmitted from the solid surfaces on its own, and it's effectively the propulsion force in the other direction. So just going back to the maximizing of the linear velocity, what we're saying for that point is that if the fluid comes in the back of the boat and goes out the back of the boat, you can add the two velocities together. If the fluid comes in from the front and goes out the back, you take one away from the other. If the fluid comes straight up with no bend on it and goes straight out, then you can neglect the inlet velocity effect. So this is a free body diagram of the forces acting on the hull of the boat, acting on the boat in its entirety. And if we were to apply Newton's second law of motion, force equals mass by acceleration, we'll see mass by acceleration equals propulsion force minus the drag force. We can neglect the pressure term here because when you work that out for your design, it's negligible. So taking the mass across leaves acceleration on its own. So we've got an expression for acceleration. It equals propulsion force minus drag force divided by the mass of the boat. So once we know the acceleration, that equals the change in velocity over time. So rearranging this expression, we get the second velocity equals the initial velocity plus the acceleration multiplied by the time step. And it's this expression here that we will use in the Excel sheet to calculate the velocity of the boat as it moves through the water. And we will be producing these types of response curves here for the velocity. So this, so you'll have your first pipe design without the nozzle. You'll have your improved pipe design with the nozzle, and you can calculate what the percentage increase was at the steady state values here. Okay, so I will open up this spreadsheet in a few moments and explain how it works in detail. But let me just give you a quick overview. It was put together by Jan a number of years ago when the project was being designed. So what you have is you've a table of properties, and that's filled in as an example, but you can fill it in for your design. Those values feed in over here to calculate the drag force, the propulsion force, and from that the acceleration, and from that the velocity. You can have a running total of the distance covered and a running total of the time to reach that distance. The table in the middle is referred to as the analytical solution. It was put together using an online computational tool called Wolfram. So it uses complex state equations, but it ultimately was used to verify the pneumatic solution. So we can largely ignore it, but we will be referring to the time step here. So you've got these response curves here, and basically they're going to take the velocity in this column against the time in this column for your two designs and represent it like this. You're going to have the drag force, which is in blue, and the propulsion force, which is in orange on this response diagram. And basically what we see is as the boat is accelerating like this, the drag force increases until the drag force meets the propulsion force. And that's where we have steady state velocity. So you want to find out what that steady state velocity is and see if it can replicate that in the test section. Your distance covered and your time to target will give you an indication of how long you need to let your boat run for before it starts hitting steady state as well. So I'll open up the actual spreadsheet and go through it in a little bit more detail now. Okay, so this is the Excel sheet. And the first thing to do is to fill in the properties table over here. You've got the acceleration due to gravity, which is a constant. You've got the density of the fluid, so you don't need to change them. The fourth cell down is the volumetric flow rate that's taken from your HQ diagram from stage 2 in meters cubed per second. In this particular case, it's also typed in liters per minute, which you probably won't need. You've got m dot, which is essentially the volumetric flow rate in meters cubed per second multiplied by the density. And then you can neglect the pressure terms here. And what you've got down at this point is the pipe diameter. So it's about 8 millimeters. And then the outlet pipe diameter with the nozzle. So whatever value you gave to your nozzle, it could be 4 millimeters, for example. You've got the mass of the boat. You can get that from SolidWorks, or you can actually weigh it. There's a scales in the lab. You've got the coefficient of drag, which you need to calculate. Gone through that already. And the frontal area. And I've gone through that as well. You've got the area of the pipe that's using the 8 mil diameter. And you've got the area of the nozzle. So once again, whatever diameter you gave that. The velocity is taking the volumetric flow rate and the area. So for the outlet, it's taking the volumetric flow rate and the area of the nozzle. And for the inlet, it's taking the volumetric flow rate and the area of the pipe. You can ignore these A and B values down the end. They were used in the analytical solution. So over here, the first thing to calculate is the drag force. And in the drag force, it's half times, if we look at the equation again, it's half times the coefficient of drag by the density of the fluid, by the frontal area, by the velocity of the boat squared. So we have the coefficient of drag over here, density, and the frontal area. What we don't have is the velocity of the boat, first of all. So initially, your drag force will be 0. And on the graph up here, it will be floored on the bottom. Next, you've got the propulsion force, and that's simply the mass flow rate of the boat, which we get from the properties table over here again, is multiplied by the products of the sum of the inlet and outlet velocities down here. So that will stay constant. But that will be a straight line up here. So the acceleration then is, if we look at this equation, you've got the propulsion force minus the drag force. We divide that by mass, we get an expression for acceleration. So that's what you type in here. It's propulsion force minus drag force divided by the mass of the boat. Copy all the way down. When it comes to the velocity, if we have the initial velocity as 0, and then the second velocity, looking at this expression, the second velocity equals the first velocity, which is the 0 here, plus the acceleration, so that's this acceleration there, plus the time step, and that's the difference between these two cells. When it comes to the next velocity, it's taking the initial velocity as the one before it, and it's taking the acceleration as this value here, and the time step that's moving on at this point. So you keep that running all the way down. You can also have, you can get this from your velocity, you can get the distance covered and the time to target. If you look down along the graph here, you probably see around 2 seconds and about 0.5 meter, it starts to reach steady state velocity. at about somewhere between 380 millimeters a second. So it's almost about a foot in length per second, which sounds reasonable. 380. So these are based on values that I put in here. So after about 2 seconds, it starts reaching steady state, and it's around somewhere between 350 mil, 400 mil per second. Again, based on these very, very average values that I put in, that sounds plausible. So just make sure that it sounds plausible for you. You can let your boat run through the test section for about a half a meter, and then let it run for 2 meters and calculate that velocity. And see, does it compare to your steady state velocity value up here? As I mentioned earlier on, propulsion force will, the drag force will start to increase as the boat is accelerating. And then when the drag force equals the propulsion force, you will have steady state velocity there. And that's what we want to calculate. Okay, so best of luck to everyone. And thanks very much for all the cooperation so far. Hope you're enjoying the project.